Okay, let's go ahead and get started with section 3.3. In this section, we are just going to go through several examples of doing a chi-square goodness of fit test. Okay, let's go ahead and get started then. So these tests are sometimes just shortened to chi-square tests. However, there are a variety of tests that use the chi-square distribution. Therefore, statisticians refer to the particular test that we're looking at here as a goodness of fit test. So let us consider example 3.3.1. This is the Boston Medical Center example. This study was centered around the scheduling of elective surgeries over a 2-year period of time. Now, scheduling surgeries is an important component of patient satisfaction and also of healthcare management. The medical center made a significant change in their approach to scheduling these elective surgeries between year 1 and year 2. So there's 2 goals that we're going to consider here. Number 1, determine whether or not the number of elective surgeries is indeed inconsistent throughout year 1. And then number 2, determine whether or not these changes were successful in making the number of elective surgeries per month more consistent in year 2 than in year 1. So let us consider the data for the year 1. This data was actually provided on a PowerPoint slide here. So we're going to need to take this data and pull it into our spreadsheet in order to conduct the analysis. Now we can see that the data or the chart here starts in September. There were a total of 25 elective surgeries here in September. And then it jumped up to 41 in October, came back down to 33 in November, and then proceeded here throughout the remaining rest of that year. There is quite a dip here at February. They only had 19 elective surgeries in February for some reason. Also, it appears that there are indeed maybe higher numbers of elective surgeries here in the summertime as well. Now again, it would be optimal to have these elective surgeries consistent throughout the year, especially for staffing considerations. So let's go ahead and take these numbers. There's actually 12 categories here. So let's go ahead and take these numbers and put them into a spreadsheet. And I've already done that. So we'll look at these here. So maybe take a minute if you want to create your own spreadsheet. You can go ahead and do that. I will go ahead and post this spreadsheet on the course website as well. Okay, so what is the research question here? Well, the research question is there evidence to suggest that the number of elective surgeries are inconsistent throughout year 1 at this particular medical facility? There's going to be a total of 12 different parameters. We're going to have a probability or a proportion for each month, September, October, November, all the way through August. Now we're going to set up the simulation model, or we go into this analysis assuming that the surgeries were consistent. So the null hypothesis here is that each of those percentages are at 8.33%. Each of those parameter values will be set to 8.33%. 8.33% is just coming from 1/12, or 1 divided by 12. So let's go ahead and look at the observed numbers for a moment. In fact, I actually created a graph here. This is a segmented bar graph. I thought I'd take a minute and show you how to create one of these in Google Sheets. So let's go back over to the spreadsheet where I have the data typed in. So I can see that I have the months across here, September through August. I have the observed counts here that have been highlighted in yellow. Those are 25, 41, 33, all the way through 44 there. Now, when computing the expected quantities, we're going to need the total. So you can simply add these up and there's a total of 429 elective surgeries in this first year. So let me show you how to create that segmented bar graph. What you're going to want to do is highlight all of the different months and then the observed counts. And then we're going to go under, I think it's Insert Chart. And the first graph that pops up is not what we're looking for. But underneath Chart Type here, you can select these segmented bar graphs. So for example, this one right here is the one that I have selected. And then that's going to go ahead and plot the observed values here. You can see that the legend here, the blue, that first box is for September, the red is for October, all the way through here. So Google Sheets used a variety of colors here. I went ahead and just changed those to a grayscale in the notes. Now you can put the counts on this segmented bar graph as well. And to do that, I need to go underneath Customize. And then I think it's the Series. So underneath the Series tab here, you just want to specify the data labels. So now those counts will be put into that segmented bar graph. So there's the 25, the 41, all the way down through. So these are the observed numbers. You could make, or you could go ahead and include the expected numbers as well underneath here. And you'll see in a moment that I had some graphs created where I had the observed counts and then also the expected counts. To change the colors, all I need to do is select on that particular cell there. So I'm selecting on September's. And then underneath the Series tab, I can change the color here to, say, a grayscale if you wanted. To get out of that editing box, just click X up here. And you can slide that graph out of the way so you can see your numbers. So that's how to create a segmented bar graph in Google Sheets. Now, let's go ahead and answer the questions here on the bottom of this page. Which month had the most surgeries? So we just need to, we can either look at the graph here or we can look at the numbers up above, but I think it was July had the most. So July had the most at 45 surgeries. How about the least? Which month had the least surgeries? I think that was February. So February here, it was only at 19. So February had only 19 surgeries. Now I don't know enough about the situation of this data, but maybe February was purposely meant to be lower. Maybe that's a common month when, say, the doctor tends to take off or something. Maybe they vacation in the Caribbean during February or something. So there might be a good reason why February actually has a reduced number of surgeries here. How about the second question then? Does it appear that the surgeries are consistent from month to month? Well, there seems to be quite a bit of variation here. I mean, that's kind of a subjective question at this point. Certainly 19, the February is certainly the skinniest bar here. And the July and August seem to be pretty large. So does it appear that the surgeries are consistent? I'm going to say not so much. Looks like there is an opportunity for making improvements. So some months seem to be quite a bit higher than others, and then that February kind of sticks out as being substantially lower as well. All right, so how do we continue with the analysis? Well, we're going to need to compute the expected quantity. Okay, and the expected quantity for this particular situation is actually going to be the same for all of the different months, because I'm trying to figure out whether or not I have inconsistencies across the months. So we set up that null hypothesis again, or excuse me, we set up the expected quantities underneath that null hypothesis. And if we go back up there and look at that a minute, it's where each of those months or each of those parameter settings were set to 1/12. So I need to simply compute the total, which is 429, and multiply that by 1/12. And when I do that, I get the value 35.75. And that's going to be the same for all of those. So let's go ahead and go back into my spreadsheet here and enter in the expected quantities here. I think I can get rid of my graph at this point. So equal, what was it, 429 times 1/12. So equal 429 times 1/12 there. Go ahead and hit enter. And then I'm just going to drag that value across so I don't have to type it in lots of times. I'm just going to drag that value across all of the months. In the notes, it looks like I had highlighted those kind of an orangey color for you, just to differentiate those from the expected quantities. Okay, so let's go back. That's how the expected quantities are computed. So the purpose of this test, again, is to compare the observed counts to the expected counts when we acknowledge the fact that inherent variation exists from sample to sample. A scheduling process should allow for some inherent variation. Certainly people are going to get sick and cancel their appointments and things like that. The chi-square test will determine whether or not the difference between the observed and expected counts is extreme enough to suggest that the scheduling system should be improved upon. So remember that inherent variation that is going to exist from sample to sample here. So it's not just as simple as looking at, are the expected quantities different than the observed? Or at least when we do that, we want to take into consideration this inherent variation that we know is going to exist in this system. And the chi-square goodness of fit test does indeed do that. All right, how do we compute the p-value then? Well, the p-value can be computed using the chi-test function. This is a common function. It's in Excel and Google Sheets. And all it needs is the observed counts and also the expected counts. So we have those quantities computed. Okay, so I'm going to go back over into my spreadsheet one more time and show you how to compute this value. So to get the p-value, all I need to do here is type chi-test. I need to highlight the observed counts, which for me sit in cells C3 through N3, I think it is. So this is going to be C3. Let me go ahead and back that up a little bit. I will show you what it looks like live and then talk about it. So C3 through N3, and then I need a comma, and then I need the expected counts. So equal chi-test, the cells that contain the observed counts, and then the cells that contain the expected counts. And when I hit enter, the value that is returned is the p-value. So let me go ahead and just show you that there. Put that on the screen for you. Equal chi-test, C3 through N3, and then I need that comma there to separate the observed from the expected, and then the C4 through the N4. And when we do that again, I'll do it one more time for you. You're going to get the p-value returned out. So in the background here, it is doing lots and lots and lots of calculations for me. Remember, it is computing the distance between the observed and the expected. It's squaring it. It's dividing that by the expected. It's doing that for all of these categories all the way along here. And then it's adding that up. And then furthermore, it's going to use a reference distribution to determine how extreme that quantity is, how extreme that total, we called that the test statistic, how extreme that test statistic is against situations in which they were equal across the 12 months. So there's a lot of work going on in the background, and thank goodness the spreadsheet is taking care of all of that for me. So let's go back to the notes then. So once I have my p-value, I'm ready to go here. I can complete the rest of my test. So what is the p-value for this test? 0.0567. Is the decision then is simply, is 0.0567 less than 0.05? No, it's not. It's very, very close, as I'll mention here in a minute. We'll talk about that. But technically, no, it's not. So technically, our decision should be that there's not enough evidence for the research question. And then writing our conclusion with the three components. There is not enough evidence to suggest that the number of elective surgeries are inconsistent throughout year one for the Boston Medical Center. The reported p-value for this analysis, 0.0567. Now, the p-value computed here is very close to that 0.05 threshold. So the Boston Medical Center healthcare administrators went ahead and decided to make some changes to the scheduling system. They thought that that was close enough to the 0.05 threshold that changes were warranted. And I would agree with that suggestion. Other things here, other comments. The practical interpretation of an outcome such as this should be carefully considered. So we haven't talked about this yet, and I need to. In particular, when I say, or when the statement is made, that we do not have enough evidence to say the surgeries are inconsistent. So that's the conclusion that we made up here. There is not enough evidence to say that the surgeries are inconsistent. So we got a little bit of double negative language there that we're using. We need to be careful with that. So when I say not enough evidence to say surgeries are inconsistent, that is not the same thing as I have enough evidence to say surgeries are consistent, or that I have strong evidence to suggest surgeries are consistent. Now, such a statement like this is similar to our judicial system. So consider the fact that a not guilty verdict is returned by a jury. This is not the same thing as the jury saying that the person was innocent. A not guilty outcome simply means that there was not enough evidence to return a guilty verdict. So sometimes innocent people, sometimes guilty people actually can get off, right? Because there's just not enough evidence to convict them. So that threshold for having strong evidence or indisputable evidence is what we use in the judicial system. That's akin to using a very strict 0.05 cutoff in our statistical decision making. Okay, a couple of other things here real quickly. This test is a composite test that considers all the categories collectively. The chi-square test goodness of fit does not, at least not directly, tell me how much each category contributes to the outcome of the test. A cell contribution calculation does, though. And what we mean by the cell contribution is just that quantity that we computed earlier in section 3.2. that observed minus expected squared divided by expected. This is referred to as the cell contribution to the overall test statistic. Those calculations were done here. Okay, so the 3.23, how was that obtained? I simply took 25 minus 35.75. I squared it, and then I divided that quantity by the 35.75. So September here is pretty far off from the expected. If we remember February here is at 7.85. Again, we know that one is pretty far off from the expected. So this 7.85, or the cell contribution from February, is a pretty substantial part of this 19. So the test statistic here is this 19.25. It is those values added up. Okay, so that 7.85 is a pretty substantial part of that 19. So one of the main reasons that I had a fairly small p-value was because of February, and also because of September. Something like January was right on target, so that one is not contributing very much to that overall value of 19.25. Another thing that we could do is look at what's called a control chart. And this is just a visual approach to identify which months are statistically unusual or unlikely against the situation in which surgeries are consistent. Now I am looking at 12 different months here. So if I apply the Bonferroni correction factor that we talked about in section 3.2, I'm going to take that 0.05 and divide by 12 there. Excuse me, I think we talked about that in section 3.1, not in 3.2. So if you're not sure about what the Bonferroni's correction is about, why don't you go back to the notes that are for section 3.1. That is discussed briefly there. Essentially, again, what we're doing is just taking the standard 0.05, the golden rule that we used, and dividing that quantity by 12. 12 because I'm considering 12 different months. Okay, so the error rate when I use Bonferroni's correction here is 0.004. Now, when I'm using the reference distribution app, okay, I'm going to put, 1/12 in for the probability of success. I had 429 surgeries. I went ahead and generated 1,000 repeated outcomes here. And I'm looking for a cutoff value that is close to that 0.004167, I guess. So 19 happens to be that cutoff for me. 19, this is a two-sided again, so 19 and 54. Now I can take those quantities, the 19 and the 54, and just put those on my line graph that was provided. So I can go ahead and take this pyramid, just tip it on its side here. It's the same pyramid for all the months here, so that is important. Okay, so I'm looking for consistency across all 12 months, so I know I can use the same pyramid across all of those. And that upper cutoff that I get from this distribution is commonly referred to as the upper control limit, or the UCL value. That's going to be 54 here. Again, coming from the reference distribution app up above. The lower control limit, the LCL, here is 19. That's just, again, the point on the left or lower end of the distribution that I use to separate the likely from unlikely values. So if this trend, okay, which is the number of elective surgeries throughout the year, if they tend to stay between my lower and upper control limits here, then we say that the process is in control. And if it starts to deviate outside of these bands, then we would say that the process is out of control. Now it looks like it gets pretty close to being out of control here with 19. In fact, 19 is right there on the edge of whether or not we're in or out of control. And that is one reason why that p-value, if we go back up there and look at that p-value, remember that p-value was really, really close to 0.05. Okay, so the reason that p-value is so close to that 0.05 is most likely because of 19. Now we've established that here through the use of a control chart, and we also established that through the use of computations here through the cell contribution calculations that I discussed up above here. Finally, there are online apps that are widely available that can do this test, so you don't have to use a spreadsheet. I just happened to grab one here from graphpad.com. All I need to do is just enter in my observed quantities and also my expected quantities. And just calculate now. Hit the Calculate Now button. It'll go ahead and compute the following quantities for you. The chi-square value, 19.25. So again, that's the test statistic value. We saw that value up above when we added up all of those cell contribution values. The two-tailed p-value here is 0.0567. That's exactly the same that I got in my spreadsheet. And then it's telling you by conventional criteria, this difference is considered to be not quite statistically significant. So there they're using that kind of vague language or that kind of marginal language, not quite statistically significant. The theory-based approach for obtaining the reference distribution, okay, so that approach actually uses what's called the chi-square distribution. The chi-square distribution is actually indexed by something called the degrees of freedom, which the degrees of freedom is just the number of categories minus 1. So here, I'm just showing you that if I put in the value for the degrees of freedom of 11, and I put in my test statistic value here of 19.25, I get the p-value returned. So this is using what's called the chi-square distribution in order to obtain the p-value. Or I should say the spreadsheet and the online app up here are using this theoretical distribution in order to obtain this p-value. And again, that theoretical distribution is based on an infinite number of dots. So that's the right thing to do. It's kind of the best situation that we can have. Okay, that was a lot there. We're going to go through the rest of these examples a little bit more quickly here. So let us now consider year 2 data from the Boston Medical Center. Remember I said that one of the goals was to determine whether or not things got better in year 2 compared against year 1. So the data for year 2 is provided here. Zoom that in maybe a little bit. We need to take those numbers, the 43, 48, 31, 34, all the way through 37. I need to put those into a spreadsheet. I need to first compute the expected quantity. Now notice that the number of surgeries in year 2 is slightly higher than what we saw in year 1. So I'm using 463 here because that is the total number of surgeries that occurred in year 2. I need to take 463 and multiply that by 1/12 again. So now my expected quantities for each month are at about 38 or 39. So I need to put those into my spreadsheet as well. And then I'm going to use the same equal chi-test that I used before. I'm going to put in the observed counts, comma, and then the expected counts. And when I do that, I get a p-value of 0.4293. So the p-value here is a little bit bigger than what we saw before. Is 0.4293 less than 0.05? No, it is not. So I do not have enough evidence for the research question here. So do not have enough evidence for the research question. So my standard conclusion here, probably getting tired of listening to what those conclusions look like, but there is not enough evidence to suggest that the number of elective surgeries are inconsistent throughout year 2 for the Boston Medical Center. Now the practical interpretation here, the practical meaning of this is that the p-value from year 2, the p-value from year 2 was 0.4293, okay, is considerably larger than what I had in year 1. So the p-value from year 2 was 0.4293. That is considerably larger than what I had from year 1. In year 1, I think it was 0.0567, if I remember correctly. Therefore, in year 2, okay, in year 2, the observed counts are much closer to the expected than in year 1. All right, because that p-value is much higher. Okay, when I'm, yep, so the p-value is much higher. It's not even close at all to the 0.05. On that chi-square distribution, that test statistic, okay, is pushed back to the left. If you remember that the lower values for the test statistic meant that I was closer to the expected. And when I was really far out to the right-hand side, okay, when I'm really far out to the right-hand side, I have a smaller p-value because I don't have very many dots as extreme or more extreme than that. So in year 1, I was more extreme than I was in year 2. All right, so this suggests that the changes that were made to the scheduling system were indeed an improvement. You can kind of see that on the trend line that's provided here as well. Okay, so there's the trend line. The red there is the expected quantity, and you can see that it matches it pretty closely. I don't have that 19 dropping out again. I did not include the upper and lower control limits on this one, but you can kind of tell that we're a little bit tighter to that red line than we were up above with the other example. Okay, so that does it for our Boston Medical Center then. Example, the changes that were made to the scheduling system appeared to be improvements in the right direction. All right, let's talk about example 3.3.3 for next. This is going to go back to the Minnesota Student Survey. In this particular example, we're going to be looking at the perceived risk of harming oneself from smoking marijuana once or twice per week. We're going to again consider this for the children from Fillmore County. Now, the perception of marijuana has certainly changed over time, as this drug was once illegal in all 50 states. However, more recently, some states have legalized marijuana, even for recreational use. So I think the state of Colorado and Washington, and I believe others, have done this. So that's certainly going to have an impact on the perceived risk of the drug. So also, in some situations, perceived risk of a harmful substance or an action differs across the genders. For example, young women tend to be much more worried about the risk of pregnancy than young men do. So it is believed that slight differences exist between genders for the perception of marijuana as well. So I'm going to consider the analysis of the female data separate from the analysis of the male data here. So let's go ahead and do the analysis for the females first. So the research question for the females: is there evidence to suggest that the perceived risk from smoking marijuana for grade 11 females from Fillmore County tends to deviate from the historical rates of other grade 11 females from the state of Minnesota? So this research question is going to look at grade 11 females from Fillmore County and compare them against individuals across the state of Minnesota, in particular women in grade 11. So I need those historical rates. I need to provide those to you in order for you to do your test. So the historical rates are defined here. About 60% of these women tend to split evenly between great and moderate risk. So when we look at the upper end of that category, the upper end there, the higher risk, about 60% divide or split evenly there. And then on the lower end, the remaining 40% tend to split pretty evenly. Okay, so you can kind of look at these numbers for the individuals in grade 11 from Fillmore County for the women here. 17 and 11, pretty, well, somewhat even, I guess, and then 16 and 20. So the expected percentages, how are those computed? Well, up above, the historical rates said that 60% tend to split evenly between great and moderate risk. So if I take that 60% and split it evenly there, I'm going to end up with 30% in each one of those groups. Likewise, if I take the 40% for the slight and no risk groups, split those evenly, I'm going to end up with 20% in each of those categories. Now, to compute the expected, I'm just going to need to take those expected percentages that I anticipate if the kids from Fillmore County are following the rest of the women across the state. And I need to multiply that by the 64. The 64 was just the total number of females, okay, the total number of grade 11 females that I have data on. So if I just multiply 64 times 0.20, I end up with the 12.8. And that's going to be the same for the slight risk category because those percentages are the same. Those counts or expected counts go up to 19.2 for the moderate and great risk categories. Let's go ahead and just answer these questions quickly. So how was the expected percent for moderate risk determined? Well, we were given information that 60%, were evenly divided between the moderate and great risk categories. Splitting this evenly results in 30% for the moderate group, and I guess 30% for the great group. How about the next question there? How is the expected number computed? Well, here I need to take the total. So the total number of individuals being considered here is, what was that total again? 64 is 64. We multiply 64 by that 0.30. So 64, if I grab a calculator here, do that math quick for you. 64 times 0.3, 19.2. So that's how that expected quantity was computed there for the 19.2 was how that expected quantity was computed for the moderate risk group. And again, that's going to be the same as the great risk group there. Oops, sorry about that. Okay, the next question. Do the observed counts tend to deviate substantially from the expected counts? So I went ahead and provided a graph for us to look at that. So if we go back up here on page 36, on the left-hand side, I got the observed counts. Okay, so it's the 17, 11, 16, 20 here. 17, 11, 16, 20. And then on the right-hand side, I got the expected counts. Again, 20% here for each of those categories and 30% here for each of those categories. And to be honest with you, at least from what I can see here, it looks like they match up pretty closely. All right, I'm a little bit higher here at 17 compared to 12.8. But just generally speaking, or I should say collectively, across all of the categories, it looks like it's pretty close. Okay, so there's not much deviation here is what I would say. So let's go ahead and answer that one. There does not appear to be much deviation from the expected counts. What does this imply about the situation here? Well, this suggests then that the trends for grade 11 females from Fillmore County are pretty close to the historical patterns or historical rates from the state of Minnesota. So being that those are so close, okay, it says that the grade 11 females from Fillmore County are pretty close to those historical patterns. So let's go ahead and compute the p-value here. The p-value, again, all I need is the observed count and the expected counts. The observed counts happen to be sitting in cells B2 through B5 here. That's what's being used here. Expected counts are in cells E2 through E5 here. Okay, so this one actually is turned vertically instead of horizontally, but that's okay. The p-value that I get out is 0.5324. Again, not even close to the 0.05 level. Okay, so let's go ahead and finish up here with this. What is the p-value for this test? Well, that p-value is 0.5324. I can say it. There we go. Sorry about that. It looks like I had a spot for that p-value. Let me go ahead and just put that where it's supposed to be. Oops. Is 0.5324 less than 0.05? No, it's not. So is 0.5324 less than 0.05? Question mark. No, it's not. Okay, so I do not have enough evidence for the research question here. Let's go ahead and highlight that for you. Do not have enough evidence for the research question. The conclusion then is there is not enough evidence to suggest that the perceived risk from smoking marijuana for the grade 11 females from Fillmore County tends to deviate from the historical rates. P-value 0.5324. So at least for the females, it looks like that their trends are pretty similar to what I would expect from other women, young women across the state. All right, let's consider the males now. Okay, so the analysis for the males. I actually have a daughter that is just finished up grade 11, so I'm curious about whether or not the men that she hangs out with, what their perceptions of marijuana are. I can't just point blank ask my daughter about this. She's not going to tell me the truth, right? She's not going to tell me if she's out smoking weed. But I can get an understanding here of what's going on, at least from this data here. So this is a personal interest to me here, just because I want to know what type of guys my daughter's hanging out with here. So is there evidence to suggest that perceived risk from smoking marijuana for grade 11 males from Fillmore County tends to deviate from the historical rates? Now, for the grade 11 males, they tend to just split evenly across all four risk levels. So remember, for the females, it was, what was it, 20%, 20%, and then 30%, 30%. But for males, it's just pretty even across the board, so 25% for each. So I need to take the data from the males. So let's go back up here and look at where was the original data here? The data from the males was 25, 10, 14, and 12. I need to put that into my spreadsheet. Okay, so let's go ahead and I did that. So there's the 25, 10, 14, and 12. There were a total of 61 males from Fillmore County that participated in this survey for this particular year. I'm putting the expected percentages evenly across all 4 categories there. All right. Where did I get 15.25? I got 15.25 by just taking 61 and dividing that by 4 or multiplying it by 0.25. Here's the side-by-side comparisons of the observed and the expected counts. Okay, now the great risk group, not too far off of what I expect. Okay, so there's a certain percentage certainly that think smoking weed is of great risk. These are grade 11 males now. For the moderate risk, it looks pretty close as well, 14 and 15. I do have some differences down here in the no risk group though. So I had 25 individuals, okay, grade 11 males, that thought smoking weed was of no risk. I should have only seen about 15. So for grade 11 males, there appears to be individuals that are more laxed about the potential harmful effects of smoking weed compared to the rest of the state of Minnesota. So do the observed counts tend to deviate substantially from the expected counts here? Well, what do we think here? They do. The counts deviate somewhat for the no risk group, but for the moderate risk and great risk, grade 11 males from Fillmore County are pretty close to the expected. So it's kind of hard to tell here. Obviously I got some areas where I deviate quite a bit, but I got other areas where I'm pretty much on target here. But that's what the test does for me. I mean, it separates or helps me define whether or not the outcomes that I see here, the pattern 25, 10, 14, 12, is that statistically far enough away from a pattern of 15, 15, 15, 15. And that's the purpose of this test. So when I go ahead and crunch these numbers or get the p-value out for the males, I'm getting a p-value of 0.0316. So again, I'm just putting in the observed counts and the expected counts into that chi-test function. So let's go ahead and finish up this one. Is there evidence to suggest that the perceived risk from smoking marijuana for grade 11 males from Fillmore County tends to deviate from the historical patterns? My p-value here is 0.0316. Need to ask myself, is 0.0316 less than 0.05? And it is this time, so yes it is. Go ahead and highlight that for you. So that does provide enough evidence for my research question. And then my conclusion is stated here as well. So there is enough evidence. Just repeat this research question, and the p-value that's associated with that is 0.0316. Okay, a couple more questions here. From the analysis done here, what can be said about students from Winona County? Okay, so I gathered information from students in Fillmore County. What can I say about students in Winona County? Well, Winona County is not within my scope of inference. Okay, so nothing, I guess. Nothing can be said about Winona County. Winona County is not within my scope of inference. What can be said about grade 8 students from Fillmore County? Again, nothing, because grade 8 students are not in my scope of inference. So who is in your scope of inference here? Oops. Who's in your scope of inference here? Well, it is grade 11 males from Fillmore County. Okay. Not just the individuals that took the survey. There were 61 of these individuals that took the survey, not just the 61. Okay, so I'm extending beyond the people that I have in my study. The scope of inference is not the same necessarily as just the people in my study. I use these 61 people from Fillmore County to try to make a decision about grade 11 males in general from Fillmore County. Now, if there is a county in Minnesota that is just like Fillmore County, okay, so it's very rural, it has the same type of demographics, then maybe I can put that county in my scope of inference, but I'd really even hesitate to do that. If you want me to talk about some other county, then give me the data from the other county. So that's the safest thing to do, is to go get data from that county if you want to put it in your scope of inference. How about the next question here? Suppose you are a school administrator for a school in Fillmore County. What actions should be taken, if any, to better inform students about the potential risks of smoking marijuana? Well, let's think about this. For the young women, they follow the trends of others women in Minnesota. Okay? But for the young men, they tend to deviate from the historical patterns. And in particular, if we go back up and look at this a minute, they tend to deviate in the wrong way. Right? I have way too many grade 11 males that think smoking weed's of no risk compared to what should have been. I saw 25, I should have only seen 15. Or if you look at the other end, the great risk, I have too few. Now granted, on the upper end, it isn't that much too few, but it is too few. Okay, so I might want to reiterate, at least to the males, about the potential harmful effects of smoking marijuana. I don't have to do that for females necessarily, because again, if we look at the trends for females, they're right on target. I mean, I guess it doesn't hurt to reiterate, okay, the potential harmful effects of smoking marijuana to the females, but they're actually okay. It's the males that need to hear this more than the females. So if I'm a school administrator, okay, I'm going to want to emphasize this to the males. So for the young men, they tend to deviate from the historical patterns in a negative way. Maybe I can add that in there. Thus, maybe one should reiterate the potential harmful effects of smoking marijuana to grade 11 males. All right, a couple of comments here. So in the analyses that we did up above here, the trends, let me go ahead and just put this onto a new page. We're going to be looking at a graph here. So in the analyses, that was done up above, the trends from the grade 11 females were compared to the historical trends for females. Okay, so I did those analyses separately, right? I looked at the grade 11 females. They were compared to historical trends for females. And then I looked at the grade 11 males and compared them to the historical trends for the males. A more direct comparison across genders may be of interest. So maybe I don't really care whether or not they're following the historical trends, but I just want to do a straight up comparison between the males and the females. Now, this can't be done with the goodness of fit test, because one of the assumptions of the goodness of fit test is that one set of the counts, in particular the expected counts, are fixed and known quantities and do not change from sample to sample. Okay, so one of these counts cannot change from sample to sample. If we go back up here and look at these numbers here are allowed to change. Okay, so next year when I repeat this study, I'm going to get slightly different values here. But when I do that, these expected counts need to be fixed and known. I need to specify what those values are. These need to be predetermined. Okay, when these are predetermined, then you're doing a goodness of fit test. So if I wanted to do a straight up comparison between the males and the females, neither set of those numbers are predetermined. I don't know how many I'm going to get here and how many I'm going to get here. In that situation, you cannot use a chi-square goodness of fit test. Now, we will be able to do this comparison if we consider Chapter 4. So Chapter 4 is going to include another chi-square test called a chi-square test of independence. Okay, so we're going to extend what we're doing here in Chapter 4 to a situation that allows us to do a direct comparison between the females and males. But as long as we're here talking about this example, let's just go ahead and talk about the apparent differences here between the females, which is on the left-hand side, and the males, which are on the right-hand side. Certainly the perceptions of the males are more lax than for the females. And this is marijuana use here. So you can see that 17 females, okay, which is about 25% of them. Okay, so 17 divided by 64. If we do that math, that's about 25%. So about 25% of the females said smoking marijuana was of no risk. But for the males, that number jumps up to about 40%. For the males, we would take 25 divided by 61. So there's quite a bit more males. There's quite a few more males. There's a larger percentage of males that think smoking weed's of no risk compared to females. As far as the slight risk group, that's the second one here. It's slightly darker gray. And for that matter, the moderate, those seem to be pretty even across. So for the slight risk, it looks like it's another 10 or 15 percentage points. Another 10 or 15 percentage points. For the moderate risk, it looks like it's about 20%. That's pretty even across both of those. 16 and 14 the counts are. Up here on the great risk, though, you can see that a larger percentage of females said smoking weed was of great risk compared to males. So the percentage for females was about 30% or so? But for males, it looks like it's only about 20%. So let's go ahead and just make a couple statements regarding those, what I just said there. So briefly discuss the apparent differences that exist in the risk of smoking marijuana across genders. So the males have males have more people, a larger percent in the no risk group, and a smaller percent and fewer, I guess, and fewer, which is a smaller percent in the great risk group. The moderate, okay, so the moderate and slight risk group are fairly even. right, looks like we took care of that question. We're just about done. Hang in there with me. We are just about done. Okay, let us consider one more situation here. The following graphic is going to look at males, okay, in grades 5, 8, and 11 from Fillmore County. So I'm going to look at just males across those 3 grades there. Here's the breakdown of the numbers there. Let's just go ahead and look at the graph. I think it's going to be the easiest here. Now for grade 5, we can see that many of the males think smoking weed's of great risk. Okay, but as they get older, as would be anticipated, that proportion goes down. So when you get into grade 8, that 43 people drop to 27 people. So if you want to use the percentages, okay, the percentage here was, what is that, about 60 or so percent? So 60% of the males in grade 5 think smoking weed's great risk. But that drops to about 40% or so in grade 8. And then that falls back even more when you go to grade 11 here. Looks like it's 20% or so in grade 11. So there's quite a decrease in the proportion of males that think smoking weed's of great risk as you go from 5th grade through 8th grade. Now, as you would anticipate, those on the other end, the no-risk group, okay, you also see that upward trend. So there's 11 here that think smoking weed's no risk in grade 5. Then it gets to about 20, and then it goes up even a little bit more to 25. One thing that's kind of interesting to me in looking at this is that when kids decide that smoking weed's of no risk, okay, so there's only 11 here in grade 5, a lot of them make that decision by grade 8. Okay, notice the big increase from 11 to 20 here between grade 5 and grade 8. Okay, we are getting more people in grade 11 that think smoking weed's of great risk. Okay, so I would imagine that some of these that thought it was a slight risk in grade 8 now have moved into the no risk category. Okay, so they probably are sliding, these people are sliding into the lower levels of risk as they get older, as I would expect. But it's kind of interesting that the no-risk group is kind of decided upon by grade 8 or so. So let's go ahead and just write a couple of comments regarding that. So the percentages for great risk drop from grade 5 to grade 8 to grade 12, or 11, excuse me. So what were those percentages again? Say about 60 to 40 to 20 roughly. It looks like it's dropping about the same amount each time. So roughly 60%. Just getting roughly 60% here. Grade 8, it drops to roughly 40%. And then in grade 11, it's down to only about 20%. The other thing that I noticed then, that at least I thought was interesting, was that the people, or the students in the no-risk group tend to make this decision by grade 8. So for the most part, there's a big change between grade 5 and grade 8 in those perceptions on that lower end. So if you're going to have a conversation with students about the potential harmful effects of marijuana, at least for boys, we should be doing that before grade 8. Catch them before they fall into that no-risk group. Okay, one last thing then here for this section 3.3 is that sometimes we have mark all that apply type questions. So some questions on surveys are much more difficult to analyze than others, and one of those examples is a mark all that apply type of question. Now, on one of the past surveys of the Minnesota Student Survey, they actually had a mark all that apply. So that question was, where have you received most of your information about alcohol and other drugs? The options there were friends, parents, brothers and sisters, churches, internet, etc. Okay, now you cannot actually use a goodness of fit chi-square test for this because the percentages, okay, do not necessarily add up to 100% here. So if you look at the data that was obtained for this, those percentages across all of these different categories don't add up to 100% here. Let me go ahead and shrink that so it's on the same page here. So it looks like lots of people said they got information from school and counselors, 67%. Quite a few from the television, 30%. Okay, 40% from parents. Those don't add up to 100%, and for that reason, I can't use a chi-square goodness of fit test. Actually, we do not have a real good process for analyzing outcomes from a mark all that apply type question. So this is a particular question that's really difficult to analyze for us statisticians. Now, maybe one of you will become a statistics major and figure this out for us. Or maybe not. But just realize that those questions cannot be analyzed using our standard procedures. Okay, that does it then for section 3.3. We will, that'll be it for chapter 3. And in chapter 4, we're going to consider situations like comparing the males and females in Fillmore County, that example that we talked about. Okay, that's it. Thank you.